Hello students, it's Dr. Marks and our topic for today is probability. We're going to do an introduction to probability, and for this lecture we're going to focus only on the basics. Now I will warn you that we're going to step it up as we do additional lectures, so it's really important that you understand these foundations that we're about to cover. So let's get started. Well, as we said, we're looking at probability. We're just looking at the basics with this lecture, but we need to have some common terminology. So one of the things we're going to do in this lecture is make sure that we have the right language for talking about probability. But then we need to think about how to calculate probability. So we're going to be doing some calculations in this lecture, but we're going to be using only some basic rules of probability. So by the end of this lecture, you're going to understand how to calculate some probabilities, the most basic forms. However, we will cover more advanced topics in additional lectures. So as I said a second ago, we need to make sure that we leave this lecture understanding the foundations. We need to start by understanding what we mean by a random event, because that's really what we're modeling with probability. When we think about a random event, a common example is rolling a die, or we might be collecting a random sample. So we've been talking about sampling a bit in this class. The thing that we need to understand when we refer to random events is that random in statistics doesn't mean haphazard. So we're not talking about the same kind of thing like completely chaotic. Not what we mean. So when we say random in statistics, we don't mean haphazard. So a good example would be a coin toss. Well, with a coin toss over many repetitions, if I keep tossing a coin over and over and over and I record the event, then we're going to see order. We can't predict, however, from one coin toss to the next, right? And that way it is random. If I flip a coin, if it's on heads, that has no information about the outcome for the next roll, rather the next toss, right? So I simply can't predict from one toss to the next. But what's going to happen is that as I continue to toss this coin, I'm going to see some patterns emerge, and those patterns are going to be based on probability. So let me make this a little clearer by showing you a graph. Now on this graph, let's look at the axes. This is coin flips. So we've got number of trials. So if you look at the x-axis, the horizontal axis, we're just going to continually flip a coin. So after each flip, we're going to calculate the proportion of heads based on all of our flips. That's what we're looking at on the vertical axis, right? The proportion. How many heads did I get? How many tails did we get? Now, we're assuming a fair coin, and when we talk about a fair coin, or you might see reference to a fair die, we're simply saying that with a fair coin, there should be 0.5 probability of heads, right? Half of the time it should land on heads. And then the same for tails. Half of the time it should land on tails. So let's take a look at this graph and see what it is that we observe. Well, as I said, we're going to continuously toss more coins, and after each toss, we're going to calculate the proportion of heads. Now you see that eventually, as we continue to toss this coin, the proportion of heads converges to 0.5. So that didn't happen on the first, second, third coin toss, right? But as I continuously toss, it's going to reach about a 0.5 probability. But it didn't seem that way on the first few tosses, right? On the first few tosses, we don't see any kind of pattern. So what I said earlier is that patterns emerge from our random events based on probability. And we do see that order here. And I could have predicted that because the order that's emerging is based on the probability of heads, of tails, right? Each outcome being 0.5 in probability of it happening. So that's what we mean by a random event, that probability helps us see the patterns and the order. Now, we need some terminology. When we talk about probability, we're talking about a value that represents the likelihood of a particular event happening, right? So in that graph before, we were looking at the probability of heads, the probability of tails, right? That's what we mean by a probability. What's the likelihood that a particular event will happen? And I know you already understand that a probability ranges from 0 to 1. Something can have a 0 probability, it can have a 1 probability. So here's my spectrum, and I'm going to let my probability range from 0 to 1. So when we talked about our coin tosses with our fair die, we had a probability of 0.5, the chance of heads on a coin toss, because with a fair die it's equally likely that it could land on heads or tails. But if I'm talking about the probability that I will get remarried in the next 12 months, well, I think that's probability 0. Currently married to somebody else who's great. So I'm thinking that's a probability of 0. Now, if we're talking about the probability that I will live in Farmville 3 months from now, well, given that I'm under contract, I'm going to be teaching at Longwood most likely, and so I'm probably going to be here with a probability of 1. But then we have things that fall in between. For example, I do study abroad every winter. Usually we're heading to Costa Rica. So if I wanted to look at the chance that I travel internationally over winter intersession, well, COVID of course has put a little monkey wrench in that, but I'm not giving it a 1 probability. I'm giving it maybe a 0.65, 0.7, something like that. Maybe I take my students, sometimes things happen and trips get canceled when there's instability or a pandemic, but I also could buy my own ticket and travel internationally. So I think there's probably at about a 0.7 probability that I'm going to travel internationally in one form or another during winter intersession. But if I'm talking about the chance that my husband will want to travel with me, well, he's not so interested. I give that about a 0.2. So you get the idea. We understand probability measures the likelihood of a particular event happening, where probabilities range from 0 to 1. Now, we all understand that probability is measuring chance, right? What's the chance that something is going to happen? So probability measures chance. In other words, how likely is it that something is going to happen? And so we have lots of examples from real life. Lots of statistics are offered to us in the form of probabilities. For example, the odds of being struck by lightning in your lifetime is apparently 1 out of 15,300. Well, isn't this just a probability because it's an odd, it's a chance? So I can calculate that the probability of getting struck by lightning in your lifetime is 0.000065. Luckily, that's pretty small. Or, what's the probability of having twins? Well, apparently the medical profession's data suggests that 1 in every 250 natural pregnancies results in twins. The word natural suggests that, okay, we have a different probability if we're talking about non-natural pregnancies. So maybe somebody has in vitro, more likely to have twins. But 1 in every 250 natural pregnancies results in twins, so we can calculate a probability, 0.004. There's an odds of 1 in 24.9 of winning a prize in Powerball, right? So the lottery. Now, it didn't say the grand prize, it just says a prize. So what's the probability of winning a prize? 0.04. But if we look at the odds of winning the jackpot, well, the jackpot in Powerball, the odds are 1 in 292.2 million. So if we calculate those odds, the probability is really infinitesimal, right? So guys, one thing I want to point out before we continue is that on quizzes and tests, if I ask you to calculate a probability, I'm looking for the decimal, right? It goes between 0 and 1. So please don't convert to percentages. Clearly we could kind of translate these into percentages, but we don't want to do that. All right, so just keep them here in this decimal form because probabilities range from 0 to 1. Now, let's say that we're drawing a name out of a hat. There could be lots of scenarios where we're drawing a name out of a hat. And let's say your name is in the hat too. Maybe it's everyone in your company. Well, what's the probability of drawing your name from the hat? We all understand that the answer to that depends on how many names are in the hat, right? So we're drawing a name out of a hat. Your name's in there. What's the probability of drawing yours? Depends on the number of names in the hat. We all understand that if there's only 4 names in the hat and you're just 1 out of 4, then there's a 25% chance. But remember, I don't want the percentage. I'm going to ask you about the probability. The probability is 0.25. But what if there are 10 names in the hat and you're just 1 out of 10? We all understand that that gives you a 10% chance, probability of 0.10. So these examples are super easy to calculate, right? And it's going to turn out that the examples in this lecture are going to be very easy to calculate. And chances are we could do these calculations without any background in probability. But it's important that by the end of the lecture that you understand probability rules. So even though we could calculate things without understanding probabilities, I'm using simple examples to illustrate the rules of probability. So please try to focus on what rule would apply, how you would calculate things using these rules, even though I know you could probably just plug it into a calculator. So I hope that makes sense. Let's go over some additional terminology. We need to learn the correct language. So what's the terminology used in probability theory? Well, the first thing that we need to think about is outcome. Outcome. So an outcome in probability is a particular result that we could have. A particular result that we could have, the outcome. So think of it kind of as the outcome of the experiment. It's a particular result we could have, and we're going to note that with B. Then we have what we call a sample space. And the sample space is the set of all particular outcomes. So our set of outcomes gives us the sample space. Then we have the events. And events are things that we're interested in. So what are the things we're interested in? So we have outcomes that could happen. We have a sample space, which is a set of all outcomes, but then we care about only certain things, those events. So we're talking about a subset of the sample space. So just those outcomes in the sample space that we care about. And so an event is something that is either true or false. It's either true or false. And we refer to events by saying event A, event B. So I know this is a little overwhelming. It's very jargonistic. We will get the hang of it. But understand what we're talking about here is, for example, the toss of a die, landing on an odd number. So we're tossing a die. That's our experiment. We care about whether it lands on odd. That's our event. And we agree it's either going to be true or false. But do we also agree there's a set of outcomes we could get from tossing a die, right? We could get 1, 2, 3, 4, 5, 6. So keep it simple. Events are the things we care about, the thing for which we're trying to calculate the probability. So let's use a gambling example because we understand that gambling is based on probability, right? gambling is all tied to probability. So we're going to use what I have pictured here, which is the American roulette wheel. And on the American roulette wheel, if you count these up, you're going to find that there are 38 different options. Now, you may see numbers only up to 36, but there's also a 0 and a double 0 that you see there in green. So all in all, there are 38 possible outcomes that our ball could land on. And in case you happen to be into roulette, just so you're clear, there's also a European roulette wheel. I didn't know that, but the European roulette wheel excludes 0, 0. So if you exclude 0, 0, do you agree it changes the odds on your roulette wheel, right? So we're just going to stick with the American roulette wheel. And so I'm going to have a number of examples where you need to be familiar with the American roulette wheel. So let me just give you a heads up that on quizzes, for example, I might refer to the American roulette wheel and you need to understand what that involves, okay? So this picture right here. All right, so let's review this terminology in relation to the American roulette wheel. Now, if we're talking about an outcome is a particular result. It could land on 1, it could land on 2, it could land on 22, it could land on 15, on 36, right? Those are all outcomes. So each individual one is an outcome. But if we look at the sample space, we're talking about the set of all possible outcomes. So if I were to list all possible outcomes, I'd have to start with 0, and then double 0, and then 1, 2, 3, 4, 5, 6, 7, 8, it goes all the way to 36. So remember, how many outcomes are there in the sample space? We said 38 rather, right? We have numbers 1 through 36, and then we have 0 and double 0. So outcome, it lands on 1, it lands on 5. Sample space, what is the list of all the possible outcomes? Then we've got events. And remember, events are those things that we're interested in, and it's going to be a subset of the sample space. So I might be betting on red. What's the probability that the ball lands on red? I might be interested in black. What's the probability that the ball lands on black or on even? Or it could also be something with multiple characteristics on a red even number. That could also be an event. So hopefully that clarifies it a little bit, that you understand the terminology outcome, sample space, and event. Now we've got to cover a little bit of notation, because there is specific notation used with probability theory. The most basic thing we're going to see is the use of PR or P, and that simply means probability. Now you're going to see me use PR. So again, probability is going to range from 0 to 1, and in between we're going to express it as a decimal. So I might wonder about the probability of event A. So I would write PR A. What's the probability of event A? Now, an outcome, we said, would be noted by B. So you see this notation here, B, and then you've got that little E next to it. B is an element, that kind of sideways pitchfork. B is an element of odd. I might say that whatever this outcome is, it's part of the odd numbers. So B is an element of odd. So E looks like an E for element. Now we've got our sample space. Remember, our sample space is all of the possible outcomes. And our sample space is noted by the Greek letter omega. So I might have this if we were looking at our American roulette wheel. Omega, our sample space, equals 0, and then 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 36. And as we said, there are 38 elements in the American roulette wheel. There are 38 different outcomes. I could say it that way. And together, those 38 elements or outcomes makes up the sample space. Note the bracket notation here. And so I'm going to try to be consistent with that as well. Then we have an event. So remember, we had outcomes. It could be a specific place where the ball lands on our roulette wheel. We have our sample space, the set of all possible outcomes, and there are 38. But then the event, and again, the event is the thing that we're interested in, the thing for which we are interested in the probability of. For example, the ball landing on odd. Well, in that case, our event is odd. So we would say that B, our outcome, is a subset of odd, and the sample space for odd would be the odd numbers on the roulette wheel, right? So B, odd, is a subset of the sample space associated with odd. Numbers 1, 3, 5, 7, 9, 11, 13, continuing on to 35. So our result B is an element of the event odd. So we've got some notation down. And again, it's just language that we use for probability. So we need to get this language down. And we'll get the hang of it. Let's move on to talk about some axioms of probabilities. So by axioms, we're really describing characteristics of probabilities. So the first one is pretty obvious, and that is that probabilities are never negative. Probabilities are never negative, right? How can you have a negative chance that something happens? That makes sense. So probabilities are never negative. So we can write this as the probability of event A, whatever A may be, is going to be greater than or equal to 0. That's how we write non-negative, right? But be clear, a probability can be 0, right? A probability can be 0. The probability that I have a third child is 0. I'm old. So that totally makes sense. Do we need to memorize this? No. It's clearly intuitive, and we just kind of instinctively understand this. The second axiom is that one of the outcomes in the sample set will definitely occur. So basically we're saying when we run our experiment, one of the outcomes has to happen. One of the outcomes has to happen. So if we flip a coin, that's our experiment, the outcomes are either heads or tails. Our sample set, our sample space, is heads or tails. And when I flip the coin, one of those has to appear, right? It would be impossible for us to not end up with a heads or a tail. So if we look at our sample space for whatever experiment we're running, one of those things has to happen. So by the same logic, if we spin a roulette wheel and the ball lands on the roulette wheel, then it's going to land on one of those 38 outcomes. Now, other than the ball like falling off the roulette wheel, let's assume that can't happen, it's going to have to land on one of the 38 outcomes. So from that, as long as I have a sample space, one of those events has to occur. Then I can say the probability of omega, which is our sample space, equals 1. The probability that one of those things in our sample space happens has to be equal to 1. So in words, the probability that something in our sample space occurs equals 1. So I know with certainty, right? Probability equals 1 means certainty. So with certainty, we know that we will get an outcome in our sample space. We don't know which one, but we will get one of them. It will be heads or tails if we're flipping a coin. All right? So those are our axioms. Nothing overly confusing there, right? It's all pretty intuitive. So now let's move on to talk about rules of probability. And we're going to cover the most simple, most basic rules in this lecture. And so rule number one is simply calculating what we call a simple probability. And gang, you already know how to do this. I really don't even need to teach you this rule because you already know it. You didn't know it was the simple probability rule, but you've been calculating it for a long, long time. So how do we compute the probability of some event A? So I want to know, what's the probability that A happens? Of course, our notation, PR of A. What is the probability of event A? Well, before we move on to the actual rule with the calculation, we need to assume some things. Here's our simplifying assumptions so that we have a simple probability. We're assuming that we have a finite number of outcomes. In other words, we are not dealing with things that are continuous. Does everyone agree that on our roulette wheel, those are a finite number of outcomes? There are only 38 things that can happen. It is not a continuum. So that's the first assumption we're making. The second assumption is that there's equal probability of the outcomes in A. Equal probability. Equal probability. So what we're saying is there's no higher probabilities for landing on black, for each individual black, than landing on each individual red, right? Each of those 38 outcomes has the same probability. So on our roulette wheel, or when we toss a die, or we draw names out of a hat, we're assuming that there's equal probability that we get a 1, 2, 3, 4, 5, 6 on the die. We have an equal probability of heads versus tails on our coin. We have equal probability on our roulette wheel that we get 1, 2, 3, or 5, 7, 23 drawing names from a hat. If there's 10 names, equal probability that we draw any individual name. So you understand then how to calculate this probability. You've been doing this over and over and over again since you could do basic math. So the probability of A simply is calculated as the number of outcomes associated with event A. So how many things fall into the set of outcomes for event A divided by the number of items in the sample set. Now you might be looking at that and going, what? But I promise you, you already know this. So let me give you an example. But we're looking at the number of outcomes associated with event A, whatever A is, divided by the number of outcomes that are in the sample set. All right. So back to our roulette wheel. We want to know, what is the probability of red in the American roulette wheel? All right. We understand then we would write that probability of red, PR, red. So first thing we have to think about, if you go back to our equation, how many possibilities are there for this event? So take a look at that roulette wheel for a second and calculate, add up, how many possibilities are there in our event? So looks like I'm starting at the top, 20, 27, 25, 12, 19, 18, 21, 16. Now I'm going towards the bottom, 23, 14, 9, 37, 32, 5, 34, 3, 36, 1. When I add those up, it turns out that event red has 18 options. So we have 18 outcomes, right? But our sample set is the whole set of outcomes, and there are 38 outcomes here. So how do I calculate the probability of red on this roulette wheel when we spin it? Well, very simply, and I know you already know how to do this, you took the number of red possibilities, which is 18, and you divided it by the total possibilities in the sample set, which was 38, to get a probability of 0.473. So we would write this, the probability of red is 0.473. So are you with me here? Does this make sense? Do you see that all we did is looked at the number of possibilities in the event space, right? Red has 18, divided by the number of outcomes in the sample set, 38. I know that you could have calculated this without knowing the equation. So that's why I'm trying to convince you. You already know the equation for calculating a simple probability. All we're doing here is adding some probability language, which I realize kind of makes it a little more complicated, but it's really nothing other than vocabulary. We're changing the vocabulary. All right, I think I've convinced you you understand this. So let's look at another one. What is the probability of number 17 in an American roulette wheel? So again, we're looking at an event equal to 17. So everyone take a second and see what you get here. So I'm going to pause. All right, if you're not done, pause your computer, and that allows us to continue on here. So does everyone agree that our event, that the number is equal to 17, has only one element, right? There's only one 17 on the roulette wheel. But the sample space has 38 possible outcomes, as we've said, if I add up all of the options. So what do? I take the number of outcomes for the event, that's just one, divide by the number of outcomes in the sample space. So 1 divided by 38 equals 0.0263. So now you have the probability of landing on number 17, or really any number for that matter. So gang, which action, if you're gambling, betting on a number versus betting on a color, do you think will have a higher payout when you're successful? So you go with your friends. If you're looking for the highest payout, which do you think has a higher payout? Betting on a number like 17 or betting on a color? Well, hopefully you understand it's betting on a number. Why? Because the probability of any one number is so much lower than the probability of landing on red. It's going to be much harder in terms of chance to land on 17 than it will be to land on red. So when I'm gambling, probability drives those payouts. So if you say I'm betting on 17, since it's low probability of landing on 17, if you're successful and you land on 17, you're going to get a much higher payoff than if you say I'm gambling on red. The probability of landing on red is a lot higher than landing on 17. So if you're successful, you're going to win, you're going to get a payout, but it's going to be a lower payout. Why? Because the payouts in gambling like this are tied to the probability. All right, let's continue. So that was our simple probability rule, something that's super easy and you already understand. Now we need to talk about the idea of disjoint events, because some events are disjoint. And when we say some events are disjoint, what we mean by that is that they cannot both occur. They cannot both occur. In other words, if A occurs, then B cannot occur. And you can understand then that's going to impact probability. If I see something about A, then that's going to impact the probability of B. But if some events are disjoint, then if A occurs, B cannot. So clearly then, if A and B are disjoint, then they share no outcomes in common. Another way of saying that is that A and B are mutually exclusive. Do we have any disjoint events on the roulette wheel? Can you see anything that would be disjoint? For example, let's say we have event red. What would be disjoint with red? Do we agree that black The event black is clearly disjoint with red. For that matter, green is as well. So if you have an outcome that is red, you cannot also have it be black. Those two are mutually exclusive. So the event of red and the event of black are disjoint. So red and black are disjoint. As we said, they share no outcomes in common. So notationally, we would say that the event of red intersected with the event of black is 0, or the null set, basically. Again, that upside down U notation means intersection. And by intersection, we mean that both occurs. So red intersected with black has nothing in common. That 0 with the slash is really called empty set. So the set of outcomes between the intersection, for the intersection of red and black, is empty. There are no outcomes in that intersection. So the intersection between red and black is empty. Null set, empty set. Some events, however, are not disjoint. So we could be working with scenarios where we have situations that are not disjoint. And if that's the case, then it's possible for both A and B to happen, because those events, A and B, share outcomes. So we could have some scenarios where we don't have disjoint events. They're not disjoint. So keep in mind, they share outcomes, which means there's overlap in the outcomes. So do we have any non-disjoint events in the roulette wheel? Well, of course we do. So let's start with red. Let's say that the first event of interest is red. Do we have any events that are non-disjoint or not disjoint? Well, how about this? Red and even. So let's say A is red and B is even. We have two possible events, and do we agree that there is overlap? Not perfect overlap, right? There's some red odd events and there are some black even events, but there is some number of events in common. So red and even would be non-disjoint. Now, it's important to understand, and this is a little confusing, so let's go through this slowly. It's important to understand that events are either identical or they are disjoint. Now, I'm not saying that's the only two possibilities, but I'm saying they cannot be both. So, events have to be either identical or disjoint. They cannot be identical and disjoint. They cannot be both. For example, the outcome 11 and 11 are identical, right? So you might be wondering, well, why would I care about that? I don't, just for illustration purposes. So the outcome of 11 is exactly equal to the outcome of 11. They are identical. But if they're identical, then they can't be disjoint, right? So if not, if 11 and 11 are not identical, if two things are not identical, then they would be disjoint. For example, 11 and 3 are not identical. And since 11 and 3 are not identical, then do we agree they must be disjoint? So 11 and 11 are identical. 11 and 3 are not identical, making 11 and 3 disjoint. So back to our previous notation, the outcome of 11 intersected with the outcome of 3 is the null set or the empty set. The intersection between these two is the empty set. So if two things are not identical, then they would be disjoint in this case. And again, disjoint means mutually exclusive. So that's a little confusing, but I think generally you probably get the sense. All right, so we understand the terminology joint and disjoint. Okay, so at this point we've gone through our probability rule number 1, which was our basic probability rule. We're about to add on a second probability rule, and that's the additive rule. So probability rule number 1 was simply our basic probability. What's the probability of landing on red on a roulette wheel? So our additive rule is a little bit different. Now we want to know the probability of event A or event B happening. We want to know the probability of event A or B happening. So we're asking about the probability of the union of A and B. So the term here, instead of intersection, now we're talking about union. Union means both, so or. Probability of the union of A and B. So union is a little confusing, right? Because you might want to say that both have to be true, that A and B have to be true. That is not what we're talking about here. I'm simply saying A happens or B happens. As long as one of them happens, then we have a true. All right. Now, for now, let's assume that A and B are disjoint. So we're simplifying our world here. A and B are disjoint. Remember, that means they are mutually exclusive. It means that there are no outcomes in common. So for the additive rule, right now, we are assuming that we want to know the probability of A or B happening where A and B have no overlap. They are disjoint. But we're going to relax this assumption in another lecture, so I'm offering you the most simple additive rule, but then we're going to have to get a little more sophisticated. So again, disjoint, red, black. They are disjoint, so maybe we want to know the probability of red or black happening. Remember, there is a green as well. Red or black happening, assuming that A and B have no overlap. Red and black have no overlap. So our terminology, our notation rather, is this. We're looking at the probability of A union B. But union doesn't mean and, it means or. And I find that a little confusing. I really have to get my brain wrapped around that. So the probability that A or B happens. So how do we calculate the probability that A or B happens? Well, it would be simply adding their probabilities. So the probability that A or B happens, A union B, is simply the probability of A plus the probability of B. Very simple. I need to just add together the probabilities. But again, we're assuming disjoint events. So for any two disjoint events, A and B, the probability that A or B happens is simply the sum of their probabilities. I'm just going to add together their probabilities. So that's the additive rule. Again, that's really easy. We will talk later about what to do if it's not disjoint, but for right now, let's enjoy the simplicity that comes with the assumption that we have disjoint events. So, an example. What's the probability of landing on 2 or 8? What's the probability of landing on 2 or 8? So notationally, remember we would write this as the probability of 2 union 8, where union doesn't mean and, it means or. And remember we said the additive rule is simply summing the individual probabilities. So the probability of 2 union 8, the probability of 2 or 8, is simply the probability of it landing on 2 plus the probability of it landing on 8. Well, we can calculate this very easily. We know that the probability of getting a 2 is 1 out of 38. The probability of getting an 8 is 1 out of 38, and that was just the basic probability rule, right? All we're using is the basic probability rule right there, rule number 1. One event, one outcome in the event, there's only one way to get 2, divided by total number of possibilities, 38. So do you see how the basic probability rule is embedded into the additive rule? All right, so when we add these together, we get 2/38, right? Which is 0.0526. The probability of getting a 2 or an 8 is 0.0526. Super easy. So what's the probability of even? And you might be thinking, well, why would I even need the probability for additive rule for this question? Well, why does that even apply, right? Because we all know that we can calculate the probability without it, right? So I know that you don't even need to know the additive rule for you to calculate this probability. But I do want to convince you that the additive rule actually does apply here, that really what you're doing is using the additive rule. So our event of even, right, our event is even, is similar to event 2 or event 4 or event 6 or event 8 or event 10 all the way down to event 36, right? We want to know the probability that we get a 2 or a 4 or a 6 or an 8 or a 10 or a 12 or 14, on and on and on, or 36, right? So we can calculate that. Our probability of even, our event being that we land on even, is simply the probability of getting a 2 plus the probability of getting 4 plus the probability of getting 6 plus the probability of getting 8 plus the probability of getting 10 and the probability of 12, on and on and on, up to adding in the probability of getting a 36. So that's really all you're doing when you're kind of computing this. You're just adding together the individual probabilities. But we also understand that each one of those is simply a basic probability. So we know that on a roulette wheel, each of those outcomes, 2, 4, 6, 8, whatever, happens with the same probability, right? There's not any that are more likely than the others. So do you agree that the probability of getting a 2 is equal to the probability of getting a 4, which is equal to the probability of getting 6, which is equal to the probability of getting an 8, which is equal to the probability of getting a 10, and so on and so on and so on, right? And we know how to use the basic probability rule, right? The basic probability rule says, for example, if we're calculating the probability of getting a 2, only one outcome gives us a 2, divided by the sample space, which is 38 outcomes. For each one of these, it would be the same, right? Each one of these has a probability of 0.0263. And now, all I'm doing is saying, look, the probability of getting a 2 is 0.0263, and the probability of getting a 4 is 0.0263, and the probability of getting a 6 is 0.0263, and so on. Well, we know that we have 18 even numbers here on the roulette wheel. So our simple math, 0.0263 plus the same thing over and over again. I'm adding it 18 times, so I can just multiply it by 18. Gives me 0.473. The probability of an even number is 0.473. Now, I know you're thinking, why would I go through all that work? Not saying you necessarily would, because we all understand it's easier to say there are 18 possibilities divided by 38, and so we're simply getting the same answer that way. But is truly the additive rule, right? And it's important that you understand this, because when we go to non-disjoint events, it's going to be a little more confusing. So it's important that you understand the additive rule for disjoint events, because when we relax that assumption, this is going to get just a little messier, and it will be confusing if you don't remember the additive rule. Now, as I just said, our additive rule that we're using right now is for disjoint events. So what would be an example of non-disjoint events? Well, what if we wanted the probability that I land on a red or an odd? A red or an odd. So remember that union means or. So what's the probability that we land on a red or we land on odd? Do you agree, folks, that red and odd are not disjoint, right? Red and odd are not disjoint. And we know that because there are some outcomes in common. If I look at the roulette wheel, I see that 1 is both odd and red, and 3 is odd and red, and 5 and 7 are odd and red, and there's some others. So the problem is that if we look at the probability of red plus the probability of odd, do you agree that we're double counting some things? We would be counting the probability of getting a 1 in both events and the probability of 3 in both events. Same with 5 and 7. So this additive rule isn't going to work. Our current rule is not going to work when we have this kind of overlap. So we're going to address what to do when we don't have disjoint events. And you're probably understanding, okay, well, I'm probably going to have to eliminate the overlap. And that's exactly right. But for right now, we're keeping things simple. I just want you to understand that this assumption of disjoint events does simplify the world. It's realistic on the American roulette wheel, but there are a lot of things in the world where events are not always disjoint. So while we have examples on the American roulette wheel that are disjoint, I just showed you we also have some that are not disjoint. So if I want to look at red and, or odd, well, now I need a different equation, but we'll go there later. All right, so now we have our basic probability rule and our additive probability rule, but you did see that we kind of used that basic probability rule in our additive calculation. So let's now add a third rule called the complement rule. And event A has a complementary event. So if we're thinking about event A, there is a complementary event to A. And it's denoted often by A with the superscript C. So event A has a complementary event A superscript C. Or it's sometimes written as tilde A, which would be actually read as not A. So we have an event A, but we also have its complement, which would be not A. So we have A and not A. So really all we're talking about with the complementary event is the outcomes in the sample set that are not in event A. So the complement to A are the outcomes in the sample set that are not in event A. So to make this a little clearer, if our event A equals odd, then what is our A complement? What's not A? Well, A complement is everything else in the sample set, right? Everything else in the sample set. So what would be not odd? Well, even, 0, 0, 0, right? Those aren't odd. So you get the idea. So in terms of a Venn diagram, this will probably make sense. That rectangle right there that we've labeled S, that's our sample space. That's all of the possibilities. So if that yellow, or rather that orange circle represents event A, then everything else in the sample space is the complement of A. It's not A. So A and not A are clearly mutually exclusive, right? So using a die, if our event is that we get a 5 or a 6, right? A, see the yellow circle? So if our event is that we get a 5 or a 6, then our complement is going to be anything that's not 5 and 6. 1, 2, 3, 4 in this case. So complement's probably pretty clear. So how would I write this? Well, I would write it as the probability of A complement, or the probability of not A. So the probability of A complement, right? Probability of the complement of A. So really, all we're calculating here is the probability of A not happening, right? So the complement captures the probability of A not happening. Well, we can use a very simple equation if we want to know the probability of event A not happening. So the probability of the complement of A is equal to 1 minus the probability of A, right? So why 1? Where am I getting that 1 from? Well, remember that axiom? That the probability that something in the sample set will happen is 1. So something in our sample set or our sample space has to happen. If I remove the probability of A, then I get the probability of everything else. So, for example, if event A happens with probability 0.38, remember everything together has a probability of 1, right? Something on the roulette wheel has to be our outcome. If I add all those up together, it's going to add to a probability of 1 because one of those things has to happen. So if A happens with a probability of 0.38, then do you agree that the probability of the complement of A has to be 1 minus 0.38, which is 0.62. So complements can be pretty handy because it tells us the probability of our event not happening. So everyone agree that we could look at examples where we say, okay, we know the probability of red. What's the probability of not getting red on the roulette wheel? So let's quickly then summarize our rules so that they're all in one place. Make sure we understand them. So we started out with rule number 1, simple probability, and that was just the probability of a single event where we have finite outcomes, where each outcome has equal probability. Heads versus tails, equal probability. 1, 2, 3, 4, 5, 6 on a die have equal probability, right? Any odd number versus any even number versus, any of those possible outcomes on the roulette wheel has an equal probability if we're looking at just one single event, a 1, a 5, a 7, a 0. So how do we calculate that? We simply look at the number of outcomes in the event divided by the outcomes in the sample space. For our American roulette wheel, we know that the denominator is 38, right? There are 38 outcomes in our sample set, our sample space for a roulette wheel. So really all we're doing there is calculating the number of outcomes in event A. If event A is that it's number 15, only one outcome gives us number 15, so it's 1 over 38. If we're looking at it being odd, I count up the odd numbers. How many possible odd outcomes are there? All right, you get that. Then we moved on to talk about our additive rule in a world when we have disjoint events, and that's important, guys. So we're looking at the probability of A or B, not and, or B happening, where A and B are disjoint events. They're mutually exclusive, no overlap. So look at our equation. A union B, the probability of that is simply the sum of the probabilities. I took probability A and added in probability B. Then we move to the complement, which is the probability of not A happening. So if A is red, what's the probability that we don't land on red? Very simple to calculate. I take 1 minus the probability of A. So there's your summary of the rules all in one place. So we need to move on and cover some additional terminology. And that is subsets. Now, I know you've covered this before, but we're going to cover it just maybe a little bit more thoroughly. Some events imply another event. And we're going to need to think about this as we kind of get a little more sophisticated in our probability. So some events imply another event because they're subsets. So we might have A, and then you've got that sideways U. So A, and then you've got that sideways U, B. Well, what does that mean? It means strict subset of. Strict subset of. So A is a strict subset of B. That's what that terminology, that notation right there is. So number 12 implies red. Everyone agree? Look at your roulette wheel. Does 12 imply red? Yes, it does, because 12 is red on the American roulette wheel. So we would say that 12 is a strict subset of red. It's one of the elements in, but we can say even more than that, right? We agree 12 is an element of red. It's part of the set of red outcomes, but it will always be less than the set of red because red is also 27, 25, 19, 18, 21, 16, so on. Do you see what I mean? So it's a strict subset. Now we've got a slightly different idea. Event A might simply be a subset of B. Now, before I used the phrase strict subset. 12 was a strict subset of red, right? It was just one part of red. But A might be a subset. That's a slightly different idea, and it's noted by this notation. We've got that sideways U, but do you see the bar under it? That's kind of an equal sign in a sense, right? So that means strict subset as opposed to strict subset, all right? And I promise you guys we're going to do some examples here because this is confusing in terms of the language. So A could be a strict subset of B, meaning they're not ever equal, like 12 is a strict subset of red, but it could also be equal to B, where A and B are equal. So with subset, it's a weaker condition because it could be a strict subset or it could be equal. Hence, the strict subset notation with the bar under it. So strict subset or equal, which gives us subset. So basically what we're saying here, if we're using the term subset, we're saying either can happen. It's either a strict subset or they're equal. Either is possible, hence the term subset. So it's a little confusing. Just make sure that you get at this point, and we'll do some examples, that A is a subset of B, not a strict subset of B. Those two things mean something very different. And it's confusing, so I'm going to illustrate. So if you're still a little confused, going, oh my God, Dr. Marsh, I don't get any of this, don't worry. I'm about to show you some pictures that will make it very clear. All right, let's look at the picture on the left, and you see that event B is always less than the outcomes in A. If you think about a Venn diagram, it falls within A. So this is what we mean by strict subset. It's always less than, it's never equal to A. So we would say B is a strict subset of A. Them being the same is not an option. That's what strict means in this case. Now let's look at subset. Look at A and look at B. Do you agree that A and B are the same? Well, now we can't call it a strict subset. We have to call it a subset. So if you look in the blue box, it says that the term subset allows for the possibility that outcomes in event A and event B are the same. Everyone agree they're the same? So A is a subset of B. Do we agree with that? A is a subset of B. It's not a strict subset. B is a subset of A. We agree with that too? But do we agree neither are strict subsets? Why are they not strict subsets? Because one does not fall solely within the other. They are the same. So subset allows the number and the actual events, outcomes in the event, to be equal. It allows them to have perfect overlap. Whereas if you go back to strict subset, one is a strict subset of the other. So again, it is confusing, but it's just terminology. So let's test ourselves here and just make sure that we understand these ideas. So I've given you three sets. We've got event A, which is 2, 4, 6. I've got event B, which is 2, 4, 6, 8. I've got event C, which has outcomes 2, 4, 6. So I'm going to ask you some true-false questions. Let's see how we do on these. First one, A is a strict subset of B. A is a strict subset of B. True or false? Everyone agree that's true because it falls within and they're never equal. So if there can never be equal and one falls within, it's strict subset. B is a subset of A. B is a subset of A. False, right? B doesn't fall within or is equal to, right? So B is not a subset of A. That is a false statement. C is a strict subset of A. C is a strict subset of A. Is that true or is that false? It would be false, right? A strict subset falls within. It's never equal. So C is not a strict subset of A, right? What could I change that to make it correct? Could I say C is a subset of A? Would that be correct? C is a subset of A? Yeah, that'd be correct. C is a strict subset of B. Is that true? C is a strict subset of B. Yeah, that's true. C falls within B and they're never equal. So that probably clears it up for you. Again, it's not a confusing idea. It's pretty simple, but it's pretty confusing to explain. But hopefully you've got that. If not, rewind this lecture just a couple minutes and review this one more time. Let's move on to some practice examples because we've covered a lot. We need to make sure we are on the right track and that you know what rule to use when you're calculating a probability.